So tonight's lesson is a follow-up to what we've been doing, working with proving different givens and inferences we can make from them. So starting off this worksheet, you'll see a do now that says using rigid motions prove that triangle ABD is congruent to triangle CBD. We've worked with this all last week. Basically, when I'm looking at my image here, I'm deciding which one of my rigid motions would work best. So we know rigid motions are either a translation, a rotation, or a reflection. All three of those transformations preserve length and angle measure. In this case, our best rigid motion to use is a reflection. We know this because they share a line, and we know a reflection has a line of reflection, otherwise known as a line of symmetry. So we're going to say it's a reflection over BD. BD is going to be the fixed points that do not move. That's why if I look at triangle ABD and triangle CBD, two of the 3 points are corresponding, aka B goes to B, D goes to D, but we're also going to include that piece that says C is going to map onto, or A is going to map onto C rather. You could do C onto A. This is not mentioned which one had to land on the other. So that's where we start. That's what we know about proving triangles so far. Now, as I go further, our goal is to figure out what properties we know about triangles and how we're going to prove them similar to what we've been doing in class lately. Triangles are arguably the most popular shape we're going to be using, especially when we're doing these formal Euclidean proofs. So when we ask what kind of rigid motion would map another triangle onto each other, we're really talking about rigid motions. That's a specific type of proof. Our formal Euclidean proofs are what we've been working around recently, when we use a given and we make a statement, or we justify a statement based off what we know or what givens we have. So really, we're going to be using triangle congruence theorems to prove why triangles would have to be equal to each other. Now remember, congruent just means it's the same figure in a different location. Like all the length and angle measures should be preserved if we have two congruent shapes. So if I get into this first one here, one of my triangle congruence methods is the side angle side method. So that's when you have two corresponding sides and the angle in between are congruent. So what I mean by that is if I'm looking here, hold on 1 second, I mean that AB is going to be congruent to A prime B prime, and AC is going to be congruent to A prime C prime, and that angle in between would be congruent to each other. That way when I read this shape, it's like having side angle side, side angle side. So that's one way. If I ever have that combination of those 3 factors, I know I can prove my triangle's congruent. So my goal for this particular proof is to try to figure out if I do have side angle side based off the picture that we used in the do now. So the first thing I want to look at here is that I want to use side angle side to prove. I'm given that AB is congruent to CB, so I'm going to make that mark the same way we do in class. AB, CB, they're congruent. The next piece that I have is that BD bisects the angle ABC. So we're talking about an angle bisector, so now I'm going to split my angle in half. So those are my 2 givens. And I'm going to set up my statement reason the same way we did in class today. So I would write that in here and write in my statement and reason. So I'm going to make myself my checklist, it's like whatever I write is my statement, my reason is just my justification along the way. So the first thing we always write down is everything that's in the given. So I have AB, the segment is congruent to CB, and I know that BD is going to bisect the angle ABC. Okay, and that's my given. Now bear with me, it's my first time trying to use this pen along well. So that's where I start this proof. So you always start with your given. And now I already know that I have a side, because it said straight in here is side. I also know that I have an angle, so I'm going to justify why I have that angle now. So I'm going to go in here, and remember my picture, I could write angle 1 and angle 2. So I'm going to say angle 1 is congruent to angle 2. And my reason here is because an angle bisector splits an angle in half. And remember, you can write anything that justifies the same means. In class, we use some different definitions, so if you use something similar but slightly different, it's all going to be okay. So splits an angle in half. Now, I have two things so far. So I have a side and I have an angle, but remember I need one more side. So one other property that we used today was anything that is overlapping, we could mark with this little X here. It's known as the reflexive property. So I can say easily that BD is congruent to BD, because basically we know that anything is congruent to itself, but this special property is known as the reflexive property. As soon as you have a side, an angle, and a side, we're able to tell my proof statement here. So I can finish this up by doing exactly what I wanted to prove here. So I can say that triangle ABD is congruent to triangle CBD. And the reason why is side angle side. So I could write that out, or I can just write SAS. So that's my first proof here to prove that two triangles are congruent. So one way we could do it is by using side angle side. As long as you get a side, an angle, and a side, the angle in between the two sides, we're good. Going on to the next possible triangle congruence method, it's angle side angle. So same idea, we have two angles that would have to be corresponding. The side in between those two angles would be congruent. So when I show that here, we can have an angle to an angle, so A prime congruent to A prime, a side and a side, and we'd have angle C congruent, so we'll give that the 2 marks. So that's one way that this could look. So we'd have side angle side in between here. Now, when I go to look at this, I know Q is the midpoint of SN, and I already have angle 1 is congruent to angle 2. So looking at that, I know right now, angle 1 congruent to angle 2, that's already given. I already have one angle. And I know I have a midpoint. So of SN, I can say that this is going to split. So we're going to have QN and SQ congruent to each other. And those two are the pieces of my given. So I'm going to start by looking at what we started off with here, my statement, my reason. We always write the given first. So you should always have Q is the midpoint of SN and angle 1 congruent to angle 2. Anything that's in this given, you're going to write down. From there, we also have SQ and NQ congruent, because a midpoint creates or cuts a segment into 2 congruent segments. You could write that it cuts it in half. Anything that gives an equivalent justification, any reason that makes sense to you, it will work. Now my final one, I need one more angle because I'm using angle side angle here. So the only other angle I could get without a given statement is vertical angle. So I know this angle is congruent to this angle. Remember, vertical angles are formed by intersecting lines. So on the opposite sides here, we get those congruent angles. So I can say angle MQN is congruent to SQR or RQS because vertical angles are congruent. As soon as I have those 3 checks, I have an angle, a side, and angle. So angle, side, angle corresponding to each other. I can say my triangles are congruent by the angle, side, angle method. So that's just another way of proving triangles congruent. One final way we're going to talk about today is side, side, side. So if I have any of the 3 sides all congruent, I can say my triangle have to be congruent to each other. So same idea. So if AB was congruent to A prime, B prime, AC congruent to A prime, C prime, and then B prime, C prime here gets the 3. We want to prove that same idea here would work in this picture. So we're going to use side, side, side to prove the next one. So right now in the following diagram we have that WY is the median of triangle XZ while having WX congruent to WZ. So right now all I know, WX, WZ, and I have to use some vocab terms. So I'm going to start off by setting up my statement reason, writing in my given. So everything in the given goes into that first statement, always. So everything it says here, you write, and your reason is that it's the given. And I only have one side, so I still need two more. I can use this new vocab term to tell me what a median is. So I know that this median, if I have a median WY, W, the vertex is connected to the opposite-soid's midpoint. So I can say Y is the midpoint of XZ because of exactly what we just said, a median connects a vertex to the opposite side. Now, if that's my midpoint, we should know our midpoint definition, and we'll know that XY is congruent to ZY because a midpoint cuts a segment in half. So now I have not only the one side here of XW and WZ, but we also have XY and YZ. So I have those two right now. The only other side that's left is the side they both share. So anytime both pieces or both triangles have the same quality you were using to prove, I can throw in my reflexive property. So WY is congruent to WY, and that would lead me to having side, side, side. So I could finish off by saying my triangles were congruent. Your last statement should always be your proof statement, and it's going to be by side, side, side. So those are the first three types of triangle congruence that we're going to talk about. Now, there are other methods, and there is going to be a challenge sometimes. Most proofs will not tell us which triangle congruence they are going to use. In exercise number 4 and exercise number 5, we're just trying to decide which one we would use. So we're not going to actually prove these even though they're set up to be proved. If you want to try practicing proving them on your own, that's totally fine. But let's just look at what we have here for the first one. In exercise number 4, we have the following diagram. BD is the perpendicular bisector of AC. And we're trying to prove the triangles CDB and ADB. So we have to think what we know about perpendicular bisector. As soon as you see bisector, we should know that that is cutting a segment into two congruent segments. So we would know we would have AD congruent to DC. You can write that out if you want. And perpendicular, by now we should have forms right angles. So we're going to have two right angles. So right now we have an angle and a side in both triangles corresponding. So to find one that we could use easily, there's no other information given, but we do have this reflexive property, BD congruent to itself. So this one would be side, angle, side. Okay? And you can explain like how we got those pieces so far, but that one would be our side, angle, side. And in exercise number 5, we're going to do the same idea. So now we have SU bisects angle RST and angle RUT. So angle bisectors, remember they split our angles in half, so I know I'm going to have two congruent angles up top and two congruent angles on the bottom. Now it was specific to say that both of them were bisected, so we can use both. If it only said one, we couldn't do the other. But similar to the last one, this is the only information I have, so we can use the reflexive again. So reflexive is going to be a major property for our proofs. We're going to really need to call on to it a lot. And then in this case, we would have angle, side, angle. Now remember, the order is so important. For these, we want the ones that are closest. You don't want to jump around and do angle, angle, side. You want to stick to the closest pattern you can, like side, side, not angle, side, side. Okay? Think about what angle, side, side spells. That's going to be one we're never going to want to use. And just as a fun fact, angle, angle, side, or side, angle, angle, order does not matter. We are going to use this eventually to prove. We'll talk about this in the future lessons, but notice it's still that pattern. Angle, angle, side. You do the ones that they're closest to. You don't want to start in the middle and then like have a blank space you're skipping over. This can't be angle, side, angle, because we want the ones closest together. And HL, hypotenuse leg, it only works for right triangles, but it's when you have a leg and a hypotenuse. So we won't worry so much about these two today, but we will talk about them in the upcoming events of the future.